What I'd like to do now is introduce to you Professor Benjamin Horton. And Professor Benjamin Horton is Director of the Earth Observatory of Singapore and a Professor in Earth Sciences at the Asian School of the Environment in Nanyang Technological University. And he's been appointed the AXA Nanyang Professor in Natural Hazards. Professor Horton led the COP26 report on managing disaster risks from natural hazards in ASEAN. He was also appointed mentor for the Commonwealth Futures Climate Research Cohort to guide a group of researchers working towards solutions for climate vulnerable communities in the lead up to COP26. Professor Horton's research concerns sea level change with the aim of understanding and integrating the external and internal mechanisms that have determined sea level changes in the past and which will shape such changes in the future. His research impacts upon important ecological, ethical, social, economic, and political problems specifically facing coastal issues. And Professor Horton's going to talk to us or give us an overview of climate change risks and impacts in Southeast Asia. So I'm very happy to hand over to you, Professor Horton.
Good morning, everybody. I'm just going to share my slides. Okay, everyone. Thank you for that introduction, Margaret. As has been stated, I'm the director of the Earth Observatory of Singapore. So this is a research centre of excellence at Nanyang Technological University. We're a big unit. We have around 150 professors, researchers, and graduate students. And our aim is to make societies in Southeast Asia safer and more sustainable. And we look at science questions related to geohazards, so the impacts of volcanoes, earthquakes, and tsunamis. And with the pending climate emergency, we look at a variety of climate processes, be they tropical cyclones that are increasing in their strength and intensity and also changing their tracks. And what I study is sea level rise. So what I'm going to do today is just give you a little bit of an introduction about how complicated it is to understand sea level rise. And then I'm going to show some projections that we have for Singapore. So in that intro to myself, one of the aspects that wasn't included was that I've also been involved in the Intergovernmental Panel on Climate Change. I was an author on the 5th assessment report, and I was a review editor on the 6th assessment report, which came out towards the last quarter of 2021. I was a review editor for the sea level chapter, which in the end, the sort of deliverable of that was to provide sea level projections for anywhere on the planet at any point in time over the next 100, 150 and 300 years. So let's try and begin. So sea level rise, like any process associated with climate, has a variety of different global, regional and local drivers. Sea level rise in Singapore, for example, is going to be very different than sea level rise in Manila or Sydney or London or New York City. But all of those cities have common global drivers, and there are two common global drivers illustrated on this schematic. On the left-hand side, is what's called a mass problem. So if you increase atmosphere and ocean temperatures, our land-based ice on our planet melts and it's transferred into the ocean basins. In the 20th century, the drivers was the melting of glaciers from the Andes, from Alaska, from the Alps, transferred into the ocean basins. In the latter part of the 20th century, in particular in the 21st century, we're getting the melting from these huge big ice sheets, and they are quite simply colossal. Greenland, for example, has enough water within it to raise global sea levels by 7 meters. But Antarctica is massive. It's twice the size of Australia. And if we compare it to Singapore, it's 20,000 times the same surface area as the island of Singapore. It's 2 to 3 kilometers thick, this land-based ice, and it has enough water within it to raise global sea levels by a colossal 60 meters. So you only need to melt a small percentage of this ice sheet to really have devastating effects. On the right-hand side is another driver, and that's a change in ocean volume. So if you increase the temperature of water through the greenhouse gas effect, the water occupies a greater space and sea level goes up. We then move on to drivers that affect the region. So why would Southeast Asia's sea levels be different from Africa or South America or Northwestern Europe? And there are two drivers here, and this sort of gets into the complexity. On the left-hand side is the driver related to the change in the surface elevation of the land. So when we're talking about sea level, not only do we need to know what the oceans are doing, we need to know what the land is doing. And this process is related to the weight that is placed upon the Earth from these colossal ice sheets. If you're underneath the ice sheets, the land subsides. If you're at the margins of the ice sheets, the land uplifts. And if you lose mass of that ice sheet, that trend changes. So if you're on the margins of the ice sheet, when the ice sheet loses mass, you become a hot spot for sea level. Second, on the right-hand side is gravity. Again, Greenland and Antarctica at our poles are colossal in mass, and anything with a colossal mass has a huge gravitational attraction. So the water on our planet is actually attracted towards the poles. When the ice sheets lose mass, that attraction weakens and the water moves towards the equator. So if you get a 1 meter contribution of sea level rise from the Greenland ice sheet, let's say, you get around a 1.3 meter rise here in Singapore, some 10,000 or so kilometers away. Then we have a series of local drivers, and these are why the city of Singapore will be different from Jakarta, from Ho Chi Minh City, from Manila within Southeast Asia. First of all, groundwater withdrawal. Many of our cities withdraw water for industrial, commercial and agricultural use from the aquifers that sit beneath the city. When you withdraw that water, the land subsides, you create a hot spot for sea level rise. That's what's currently happening in Jakarta and Manila. Manila, for example, has a rate of sea level rise that's 4 times faster than the rate here in Singapore. Second of all, in tectonically active regions, and oh my God, Southeast Asia is the most tectonically active region in the world, you have land level changes when an earthquake occurs and between earthquakes. So when an earthquake occurs, you can get rapid land subsidence, i.e. rapid sea level rise, and then in between earthquakes, you get slow uplift. All those signs can be reduced. And then finally in Southeast Asia with an island archipelago, the interaction between the ocean currents and the atmospheric currents causes sea level to pile up in certain parts of Southeast Asia during monsoon seasons, for example. So what do we do to try and understand these processes? Well, we have to do a few things. We have to go back through time. So we have to go back through the last glacial cycle. So what this graphic is illustrating to you is an animation of the globe running at 2,000 year time steps. So running from the last glacial maximum 26,000 years ago, where we had these large ice sheets in the northern hemisphere. As our climate warmed up from the glaciation, these ice sheets melted, our oceans changed in volume, and sea level rose. And we can see that throughout the globe. One of the things we did at the Earth Observatory of Singapore is we wanted to understand the record in Singapore. So we took a variety of drill rigs. We even took them from just beside Marina Bay Sands, which is one of the iconic buildings here in Singapore. From these, we can build out a picture of how sea level changed in the past. So this graphic shows time along the x-axis, the last 10,000 years, and the height of sea level. So at around 10,000 years or so ago, actually beneath Marina Bay Sands, we found a fossilized mangrove, which suggested that sea level was some 20 meters below present. As the Earth warmed up from the last glacial maximum, sea level rose very rapidly to around 5,000 years ago. We can see rates on the bottom diagram in millimeters per year, fast rates, but then stabilizing. Sea level's been stable in Singapore for some 5,000 to 6,000 years. The next type of data that we try to look at is instrumental records, records that come from tide gauges that have been placed around ports on our planet. Now, in Northwestern Europe and North America, these instrumental records stretch back hundreds of years. But in the tropics, there are no records longer than around 40 years. So it just doesn't give us the instrumental record to calibrate models of the future. So what we try to do is we try to supplement the short instrumental records with geological recorders. And what we use are coral microatolls. So coral microatolls growth is shown on this schematic. If sea level's rising, the corals grow up. If sea level's stable, the corals grow outwards. And if sea level falls, the corals expand downwards. So we did some work on the corals around Singapore, and then we could take the short instrumental records I'm showing here, stretch them back over 100 years. And we also have corals that stretch back thousands of years to give us a very long time perspective. And from that, for the first time, we could show that here in Singapore, sea levels that have been stable for 5,000 years are now starting to accelerate. Okay, finally, let's look at the projections of sea level. So once we've understood the relationship between ice sheets and oceans over the glacial cycle, once we've got an instrumental record that can calibrate our models, we can then project the future. So we look at two projections in these particular graphics. One is called, and these are from the IPCC, one's called the Shared Socio-Economic Pathway 1.9. So this is where we peak our global emissions of carbon dioxide in 2030, and then we become net neutral by about 2050. On the far right-hand side, we have the SSP 5 8.5. That's the business as usual. That's the track of emissions that we have been on since we've been doing climate model projections, beginning some 30 or so years ago in 1990. So let's look at the projections of sea level. So what we have here in the red is the 50th percentile for the high emission, in the blue is the 50th percentile for the low emission. And then in the dashed lines are rates of change. So if we just look at the 50th percentile, what facts can you draw out from that? Well, I think it's threefold. First of all, it doesn't even matter if we peak our emissions in 2030 and become carbon neutral by 2050, sea level will still rise. So all of our coastlines around the world need to adapt to sea level rise. And that's because of the long-term processes associated with the oceans and ice sheets. We've set that train in motion. We can't stop it, certainly not in the next couple of thousand years. The second point is that on the short term out to 2050, it's really a scenario independent. It doesn't really matter on the high or low emissions. We've got quite an accurate number for Singapore of around 20 centimeters. The big difference is when you get towards the end of the century, and the driver for that is the potential collapse of the Greenland or Antarctic ice sheet. Now, the IPCC also does storylines, so looking at a variety of processes and what happens if you cross a tipping point or a threshold. So we can look at that to do with coral reefs, or we can look at that to do with fresh water or food availability. We can just look at this to do with sea level rise, because there are two processes associated with our large ice sheets that could cause their catastrophic failure if we take our temperatures above 2 degrees C above the pre-industrial values, i.e. above this Paris Agreement that we have commonly talked about and was very prevalent at COP26. So two processes. First of all, marine ice shelf instability. If you warm up your ocean waters, they attack these shelves that basically buttress all the land-based ice. You collapse those shelves and the land-based ice can catastrophically enter the oceans. Marine ice cliff instability accelerates that process, that when those land-based ice entered the oceans, it enters by cliff collapse because you get calving right at the base of the glacier by wave activity. What are the impacts on sea level rise in Singapore of these very high rates? Well, if we just look at the 83rd percentile, the 1 in 4 chance, we're now getting to around 1.75 meters. And if you took this out to 2150, you'd get around 5 meters. And then sea level rise becomes an existential threat to Singapore, because it will affect the sovereignty of Singapore and many other island nations. For example, Singapore has a third of its island that's only around 1 meter above the highest tides. So you can see the potential impacts of sea level rise on this island nation. So to conclude, if you're going to study sea level rise, it's not a simple topic, but we have to understand both the present through instrumental records, commonly supplemented in the tropics by surrogate, and past records. We must monitor the glaciers, Greenland and Antarctica, these land-based ices, because they're the ones that can cause the catastrophic sea level changes. It should always be remembered that every country that has a coastline will have to adapt to sea level rise, because we've set the wheels in motion. And related to these ice sheets, we can look at the IPCC projections, but for some of our most valuable assets, we need to be aware that we can have sea level rise well in excess of 1 meter by 2100. Thank you very much.
Thank you ever so much. That was fascinating, and it's really interesting to see the data. Yeah, so thank you for that. We really appreciate getting those hard facts. They're very useful for us. And of course, there are many countries, people from many countries in this conference who have coastlines that will need to be considered as these things occur.